Hello. What's that playing? My gosh. I think it's the music from the Matrix. So I think I will follow up today by doing some sparse matrix computations. Enough of that. Okay. I'll do this. What I'm going to do now is work through two libraries. One SPDEP, which that's where I'm going to create a sparse matrix. I could, of course, just jam things into a sparse matrix and form it on the fly, but instead I think I will build it on a neighbor structure. So I'm going to use SPDEP for spatial data, and I'm going to use SPAM for the sparse matrix program. And I'll run through some things you can do with sparse matrices, give you a fast idea. The key thing is they're astoundingly fast. So let me start out by reading in a file. So here's a file name I have. It's called trees. It's an inventory of trees in Edmonton, Alberta. And it's pretty big. So let me take a look at this real fast. So I will read it in. See what's in there. Oops. Probably going to take a little teeny bit of time to get in. Trees came out of a Excel file, or comma separated variable file, basically Excel file export, which really came out of a GIS. So and let's take a fast look at it. It has a lot of variables, but most of them are empty at this point. So really what we have is, let's just look at the first line. Okay, we have latitude and longitude, bunch of blanks. There's ID owner, I won't use that. There's genus, that I can actually use. There's common name of the tree. I'm actually going to weed it down a bit to just be elms in a minute. Okay, somewhere in there's the diameter of the tree. Alrighty. So, all I'm going to try to do is work with the X and Y coordinates and make a neighbor matrix out of this. Let's take a fast peek at this anyway. It's big. Let me take a look at how big. Okay, it has 129,000 trees in it. I'm just going to do one species, so, well, one genus, really. Table. Let's see, Ulmus. That looks like that'll narrow it down to a small data set of only 56,000 records. So let's go trees equal subset of trees. Nothing sparse yet. Luckily we haven't done anything that really needs sparsity. Okay, trees, and then genus will equal Ulmus. There we go. Aha, that didn't take long. How big is this? It is a 57,000 by 26 data matrix. Okay. So the coordinates are actually the first two. And since I'm going to have to type that a couple times, I might as well make it, put it into a matrix. Okay, so let's take a fast look at these. I'll probably regret this. Here's the coordinates. I'll make them a little smaller, the dot size. So let's go CEX equals 0.4, and color equals green, because they're trees. And then let's take a look at what this ends up like. Yeah, I'm seeing the spinning ball. This could be something I decide to regret. Oh no, that's not too bad. There we are. There's Edmonton, and there's about 57,000 trees in there. Okay. All right. So what I'm going to do is I actually put in this line right here. I'm going to use a command from spdep. I already pre-ran this. It doesn't take that long, but it takes a couple minutes, and you don't want to sit around watching this thing spin. So it didn't take a really long time. What this does is it adjusts it to UTM, basically. Converts things to kilometers, north, south, and east, west, and anything between 100,000th of a kilometer, that's pretty darn close for trees, 1 centimeter apart, and what is this? Let's see. If it was 0.1, they would be 100 meters apart. So 0.05, 50 meters apart. So any of the elms that are within 50 meters, basically, are going to be considered neighbors. So it's going to create a neighbor matrix. And that matrix is big. It's going to be 57,000 by 57,000. But it's not actually creating a matrix. It's creating a neighbor structure. So NB1 is a neighbor structure. Let's go over here. I'm not going to run this because I already ran it. I'll show you what's in it. NB1. Oh, I might not even want to do that. It's NB. Oh, what the heck. Okay, I'm gonna slightly regret because it's going to show me all the ones that don't have neighbors, which will be quite the list. There we go. So let's see. Oh, holy smokes. Okay, so it says 57,000 regions or trees. They're connected by 630,000 links. So this constitutes a matrix that's about 2% filled. It's got to be actually. Oh, no. It's going to be way less than that. Oh, percent, 0.01%. Okay, that makes sense. The average tree has 11 tree neighbors within 50 meters, but there's 992 trees with no links. Well, I really don't want that, so I'm going to put in a second neighbor structure, which is a k nearest neighbor, which for each tree we'll just pick out the closest one. Oh, I should have called that NB2. That's what I wanted to do. Here, stop this thing. It doesn't take that long, but I'm going to call it NB2, just on principle. Because I called NB1 the first neighbor structure. Okay. Let's go look at those trees again. Woohoo, look at that. Pretty darn green, huh? Maybe I'll play some music from the Matrix again. Okay. I thought this ran fairly fast, the one nearest neighbors, but it could take a few seconds. Let's see. Is there something else I can look at in the meantime? Not really. Oh, wait. Hold on. I just had an idea. Oh, okay. It would have taken a little while longer to run, but I had pre-checked it a little earlier, so I have NB2 sitting there. This is like one of these cooking shows, you know, those cooking shows where they put something in the oven, but instead of waiting for it to cook, they already have one cooked inside there and pull it out. It's like, hey. So I kind of pre-formed these, but they really didn't take that long to create. Just longer than you want to sit around looking at that graph over and over again. So this is a true just nearest neighbor, so each tree has one nearest neighbor, one link, extremely sparse, so there's 60,000 regions, 60,000 non-zero links. It's non-symmetric because one tree can be the nearest neighbor of another one without the relationship going the other way around. Tree 1 can be the nearest neighbor tree 2, but tree 2 not be the nearest neighbor tree 1. That's okay. I don't need symmetry for this case. So I'm going to actually merge those two link things together. I can plot those, but I'm kind of afraid to because they have 60,000 points in them. No. When dealing with large data sets, you have to be careful of what you do. I'm going to union them together to create a combined data set. So this contains something with the links of both. I don't believe this takes very long to run, unless something catastrophic has happened to the computer since I last tried this. Okay, that's not too bad. So here's our combined one. Okay, there's no missing, there's nothing with that lacks a neighbor, or it would print them all out. So you have 60,000 regions, about 0.02% of them are of the possible links are linked. So there's 11 links per tree. Okay, and everything's linked together now. So that's my NB. Now the trouble is the class of that is something from SPDEP called a neighbor. Looks kind of neat. Let me look at the head of that. It's sort of a sparse matrix representation itself. Oops, sorry, capital NB. Let's take a fast look at those. So for instance, the first tree has these three neighbors, second tree has these three neighbors, and so on. So this is a sparse representation of the links together. Okay, so now I'm going to convert that to a matrix. I'm going to do in 2 steps. These are with commands that are from functions that are from SPDEP. Okay, this will convert into a type of list. So I'll take NB. What that does is it's going to give weight 1. So it's going to make this gigantic matrix, at least in theory. And if the ith row and jth column are trees that are neighbors, I'll put a 1 in that spot. And do I want to do 1 or do I want to column row standardize it? Decisions. I won't. I'll just put a 1 in there. Okay. And then what else? Oh, zero policy. Well, I don't need to set a zero policy because there aren't any zero policy. I'd have to set to true if I want to allow some trees to have no neighbors. But that's not an issue here because every tree has a neighbor in this structure. So that's going to give me a list W, which is a sparse representation of the neighbor structure. But now I want to convert it to a sparse matrix that can be read in SPAM and done computations done. So as SPAM, list W converts one of the things to a sparse matrix. So let's see, class W should be a sparse matrix. Yep. Let's take a peek at this. There's some nice functions. Well, let's look how big it is. The theoretical, and thank goodness it's sparse and compacted because it's a 57,000 by 57,000 matrix. If that was full, it'd be a problem. Let me display it. That should be, let me try to spell display. Display will actually show a giant, it'll be a graph that's 57,000 by 57,000 dots. That'll show me which ones are 0 and which ones are non-zero. This is the idea to get what sort of patterns are going on in your neighbor structure. Note to self. Plotting is one thing you don't necessarily want to do. It's functionally where it's almost making into a full matrix because it has to create an image that's, what is it, 57,000 by 57,000? Okay, here we go. Let me get this up here. There's the structure there. So you can see there's things along the diagonal, or things with similar numbers in the thing are neighbors to each other. So you can see little groups, but then you can see there's quite a lot of structure. It's sort of symmetric, which the nearest neighbor will be symmetric. Okay, but mainly white. So there's not many dots. There's not many connected pairs of neighbors. So this is tree number 0 to 57,000, tree number 0 to 57,000, and darkened in there if those trees are considered neighbors. All right. Too bad I don't think this does any preconditioning. There's some snappy ways to reorder the rows and columns in order to get even more of a diagonal structure, which often runs faster, but I don't think I can do that in SPAM. Not sure. So once we have it in a sparse matrix form, we're allowed to do all sorts of things. So I'll just show you the set of commands. I won't run them all because I'll just going to do some specific. But there's a cbind, an rbind, and apply. Those are really handy commands. They work just like the ones in regular R, so I can bind together as columns a bunch of sparse matrices. I can bind together as rows, stack one on top of another sparse matrices. Apply takes a sparse matrix, and if margin's 1, it computes things on the rows. Margin 2, it computes things on the columns. And I can apply a function to it, so it's apply type thing. There's a command cleanup, which sometimes comes in handy. You put in your sparse matrix and you put in a very, very small number, and anything less than in magnitude than that number is converted to a 0. So it cleans out very small non-zero numbers. That allows you to pack your matrices tighter in less room. There's determinants. You put in your sparse matrix. These are highly optimized to work with sparse matrices. They work astonishingly fast compared with how long it would take on a full matrix. And it'll compute the log of the determinant if you say logarithm equals true, which is nice because, as you saw in my example in class, I wanted to show you how long it took to compute things. They work great on a 1,000 by 1,000, but when I did a 3,000 by 3,000, it ran, but it overflowed the determinant overflowed, because determinant of a 3,000 by 3,000 matrix tends to be 10 to the 600th power or something like that. So it completely overflows. But if you compute the logarithm of the determinant directly, then you can actually pack it or compute it when the determinant itself would overflow. What else is another one? You have a command is symmetric. I could even do that one. Is symmetric. It just tests, as you might guess, whether a sparse matrix is symmetric. So, of course, everything takes, well, it's not symmetric. Okay, that didn't take that long. There's a series, almost all the math type things. There's if you apply these to a matrix, what it does, it converts the numbers, it applies this function to the numbers in the matrix. So if you do a plus, you could add, subtract, multiply. That's term by term. That's not matrix multiplication, but if you take two matrices of the same size, it takes each of the matching locations and multiplies them together. You have ceilings, which round up. You have floors, which round down. You have round. You have absolute values. You have logs. You have exponents, etc. All those commands have been optimized to work on sparse matrices. So if you apply them to a sparse matrix, you get a sparse matrix where this function's been applied to the values in the matrix. You also have matrix computation things. So matrix multiplication, add, subtract. You have transpose. By the way, you also have logical things you can test. So you can fill a matrix with logical statements. So, for instance, if you have a sparse matrix and say, is this sparse matrix greater than 2? It will produce a matrix where every spot in that matrix that's greater than 2 gets a true put in. So, okay. And a lot of other functions that look like they came from just regular row sums, row means, are optimized to work. They're spam. They're really .spam if you want to know. Okay, so they're generics that work on the sparse matrices. So you have all those type of things that they've written specifically to also work on sparse matrices. There's a solve. Solve is really nice. If you put your sparse matrix and you put a vector B, what it does is it solves the set of equations B equals W times A. So it's essentially the same as applying the inverse to B. So that's a way you can solve equations. It's probably way better than inverting. If I just say solve W, it'll invert W, but warning, the inverse of a sparse matrix is full. So it'll expand to fill its 57,000 by 57,000. Well, it probably won't even run in a reasonable time. There's a really nice command, diagonal. So when diagonal is applied to a sparse matrix, it gives you the diagonal of it. If you apply it to a vector of numbers, it creates a sparse matrix with those values down the diagonal. Okay. So let me actually do something with this. For instance, I want to find the largest eigenvalue of W. So I'm going to use in Letterman, you ever seen stupid eigenvalue tricks? It was one of his less popular routines. R. Poisson, 56,000. 9. But this is. Let's see if this works. So I want to be very careful in doing things like taking eigenvalue. I certainly don't want all 56,000 or 57,000 eigenvalues from this matrix. That could take a while. So what I'm going to do is generate a whole slew of how do I want to do this? Yeah, that should work. So I'm going to create a whole slew of random Poisson variables, 57,000. So, oops, I don't want to put that in W though. Yikes, I almost overwrote my matrix. Okay, in Y. And I'm going to do a stupid matrix trick. So it turns out if you take W times Y, if Y was an eigenvector of W, you'd get Y back times an eigenvalue. So a good trick to find the largest eigenvector is I'll repeatedly multiply W by Y. I'll multiply W by Y. I'll take the result of that, multiply W by that. Take the result of that, multiply it by W, and so on. And I'm going to normalize it each time I do that. And what it'll do is very rapidly that Y will head to the eigenvector that's associated with the largest eigenvalue. So that is one way to numerically compute that. It turns out these sparse multiplications are fast. Oops. Okay, so let's show how we'll do this. So we'll do Y old equals, we'll keep standardizing it. So Y over the square root of sum of Y squared. Probably could have done it snappier. So I standardize it to be length 1. Y old is length 1. Now I'll take Y new is W, my sparse matrix, times Y old. Multiplication by a sparse matrix is really fast. So I get this new vector. Then I compare how big the new vector is, just the first item in it, with the old vector. That should give me an idea. Once it converges to an eigenvector, that'll show me what the eigenvalue is. And then I say Y old is Y new. What was old is now new. Okay. And then I just repeat this a few times. I should have written this as a function, but what the heck. So I'll re-standardize again. Huh. Okay, let me pause here. Is it not changing? Oh, for goodness sakes. Of course it's not. Okay, hold on. Error, error, error. It's Y old that I want to standardize, so here we go. There, that could explain it. So I'll standardize Y old. I bet you saw that and are yelling at your screen. Ron, you standardized Y. You kept standardizing Y, not Y old. Okay, so I take the old version of the vector, standardize it. Then I multiply W by it. Okay. Now, Oh, wow, it looks pretty close, converging very rapidly. It's looking like the largest eigenvalue is about 3. Yep. So notice it's oscillating around 3, but getting very, very close to it. Okay, there we go. So the largest eigenvalue of W is 3. There's actually a theorem that told me that, because it's a matrix that has 1s and 0s in it. You can directly calculate the eigenvalue, but this is nice. So I use repeated multiples by W. Actually, Y old, not that I want to look at, because there's 57,000 values in it. But it's the principal component, basically, that goes with the largest eigenvalue. So, see? It's not usually easy to work with 57,000 by 57,000 matrices, but vector multiplication is fine. So, the rule of thumb is if I want, so I'm going to create one last thing, and then I'm about to stop. So, I want to create an identity matrix with diagonals of 1. Here's how I would do that. So, let's reiterate. The largest value of W is 3.0. Actually, okay. So I'm going to use that fact in just a minute. So I'm going to do almost one last thing. In some spatial models, you have to compute identity matrix minus a constant times W. And the constant has to be less than 1 over the largest eigenvalue. So I'm going to finish a little computation just to show that what would normally be hideous computations with large matrices or full matrices aren't so bad with sparse matrices. So I'm going to use diagonal. So diag is going to give me matrix. I'm just going to put a list of 1s. I'm going to put 56,959 1s in a diagonal matrix. There we go. And that's really sparse. I won't even bother taking the display. It only has values down the diagonal. And for instance, I might create this sparse matrix. Oh boy, I want to not print it out. Don't print anything out. So, for instance, in some spatial computations, I'll need an alpha. So I want alpha, it turns out technically has to be less than 1/3, so let's go 0.2. Okay. And then I do a computation, alpha times W, matrix multiplication, transpose of I minus alpha times W. Again, you can't imagine how vile this would be if these weren't sparse matrices. I'd be multiplying 57,000 by 57,000 matrices by each other. This thing should end up not quite as sparse, but still pretty sparse. Oh, there it is. This could take a little while. And then I'll take the determinant of it, and really those are the key parts I would need to do maximum likelihood analysis in certain spatial models like conditional autoregressive models and such. So the key thing is I just wanted to show you that you can take in SPDEP, for instance, find a neighbor structure from GIS data, and those are perfect types of things for making sparse matrices, because typically the number of neighbors is small compared with the size of the entire data set. And it just shows once I've converted something to a sparse matrix, and in the handout I show how I do create one of those just from scratch. But once I create a sparse matrix, I can do computations as long as I'm careful about the order I do things or what computations I do. I can do computations without it blowing up. Okay, here we go. Oh, right, it actually looks a lot the same. V, even though this matrix has been multiplied by itself, it's actually a little bit more scattered around the diagonal because I've probably doubled the number of non-zero values. Okay.